Hi everyone. Today I'm going to introduce our recent work, PSLA, improving audio tagging with pre-training, sampling, labeling, and aggregation. My name is Yuan Gong, and this is a joint work with Yuan Chong, James Glass, and we are from the MIT Computer Science and Artificial Intelligence Laboratory. As we know, audio tagging is an active research area and has a wide range of applications. In order to get a good performance for audio tagging, we basically need three things. The first thing is we need to have a strong model, and second thing is we need a good data set. And we also want to say that we need an appropriate training pipeline. So for the model, we already have a lot of recent research, including PSLA, PANS, deep res, and audio transformer. And for data set, we have large scale AudioSet, FSD50K, as well as small scale ES50 and vocal sound. But we are looking at work introducing the training pipeline for audio tagging. And that is the motivation of this work. We want to introduce a collection of training techniques, and we call it PSLA. PSLA is a collection of existing training techniques. So as the name suggests, it includes four components. The first component is cross-model pre-training. The second component is balance sampling and data augmentation. And the third component is label enhancement. And the fourth component is model aggregation. And we test our PSLA model mainly on this model architecture. It's generally based on EfficientNet and attention polling module. It has around 30 million parameters, which is much smaller than the state-of-the-art model. Let's first talk about cross-model pre-training. In audio tagging area, in-domain supervised and self-supervised pre-training has been extensively studied. But we need large-scale audio data for either self-supervised training or supervised training. But we found that pre-training with ImageNet data set also improved the audio task performance, and that we don't need any in-domain audio data. Further, in practice, many commonly used DN architectures, for example, ResNet, EfficientNet, and Transformer, have off-the-shelf ImageNet pre-trained models. That means it is almost free for audio-to-speech research. And on the left hand, I'm showing a curve that is the relationship between the performance improvement versus the in-domain training data. And we find that ImageNet pre-training always improve the performance, even when the in-domain training data is the massive 2M for AudioSet. And next, let's talk about balance sampling. AudioSet and other audio data set are generally class imbalanced. So we apply a balance sampling strategy to alleviate this problem. We first count the total sample number of each class and use its receptor as the weight of the class. And then we sum up the weight of each class for all labels that the clip is annotated. That means for each sound class, the fewer the sample number, the higher the weight. And for each audio clip, the more labels it is annotated, the higher the weight. We also apply data augmentation to the input. The first technique we apply is spectrogram augmentation. That is, we randomly mask a time span or frequency span. And we also apply mix-up training. That means we add up two audio clips and also adds up their labels. with a factor of lambda. The third component of PSLA is label enhancement. That is from an observation. On the left hand, I plot the average position, namely the performance of each class. We find that the speech class has a much higher average position than the male speech, female speech, and child speech classes, while they should be quite similar. And further, we found that in the AudioSet, the speech class have around 1 million samples, while the sum of male speech, female speech, and child speech only has about 34,000 samples. That means only 3.7 of speech samples are labeled as either male, female, or child speech in the full AudioSet. Ideally, the number should be around 100%, but that's actually 3.7%, which means potentially there's a larger number of samples are missing labels. It's not the only case we find in the AudioSet. Similarly, the music class has a much higher average position than heavy music and sad music class. Singing and song have similar definition, but very different average position. So then we identified two types of labeling error in the dataset. That is type 1 error, that is an audio clip is labeled with a parent class, but not also labeled as a child class where it does in fact contain the audio band of the child class. And type 2 error, an audio clip is labeled with a child class, but not labeled with corresponding parent class. And then we propose an ontology-based label enhancement method. Basically, the method we propose only add more labels to the original label set. We do not remove any label from the original label set. And for each audio sample, we check the prediction of a model trained with original label set and search its parent and child classes. If the model's prediction on the parent and child classes are above certain threshold, we add the label of the parent and child classes. So that's generally it. Let's see the result. We show the label enhancement or LE in short with different label enhancement strengths. It is the threshold to change the label. The lower the threshold, the stronger. We found that the model trained with enhanced AudioSet labels consistently outperforms the model trained with the original label set. All evaluation sets except the original AudioSet evaluation set. That is potentially due to the AudioSet evaluation set itself contains annotation errors, and the error is in the same distribution with the training data. So if we change the distribution of the label set in the training data, that doesn't lead to a performance improvement on the test data. The final component of PSLA is model aggregation. So namely, we explore two techniques. The first technique is ensemble. And specifically, we tried 3 ensemble strategies. The first strategy is we call checkpoint ensemble. Namely, we only run experiments once, but we save the checkpoint model every epoch, and then we average the prediction of every checkpoint model. And as we can see, this simple method can also noticeably improve model performance. The second ensemble method we tested is multi-run with same setting. Namely, we run the experiment 3 times with different random seed, but using exactly the same setting. And then we ensemble the final model of each run. And we see that we get more performance improvement with fewer number of ensemble models. The third ensemble method we tested is we train the model multiple times And each time we use a slightly different setting. As we can see, this ensemble method lead to the largest performance improvement. So the conclusion is we need diversity in the model. But just using the simplest method, just run the model once, it still can improve the performance noticeably. And on the right hand, I'm showing the performance improvement led by the weight averaging. As we can see, the performance improvement is minor, but it's consistent. In that figure, I show the model we aggregate. As we can see, for weight averaging, it's generally better to average weight from checkpoint model of the 10th epoch to the end. While for ensemble, it's always better to include more models. Even with ensemble, the first checkpoint model to the last checkpoint model, it leads to the best performance. So we also found that PSLA is model agnostic. While all previous experiments are based on the EfficientNet model we just introduced, we have checked its performance on a variety of different models, including MobileNet, EfficientNet of a different size, like a model without attention pooling, and ResNet. And after this work, we also test PSLA on a transformer model that also noticeably improved the model performance. So the conclusion is PSLA is model agnostic. It improves the performance of all models we evaluated, including MobileNet, EfficientNet, ResNet, and transformer, with or without the attention module. And we also check the contribution of each component we propose. And we found that removing any component from the PSLA lead to a performance drop, which and on both balanced and full AudioSet, as well as the FSD50K dataset. So, which means all components contributes to the performance improvement. And if we check the contribution, we find that balanced sampling leads to the largest performance improvement for AudioSet. And besides balanced sampling, the rank of contribution is sorted in this way. The largest is Pretraining, and the second is ensemble, the third is masking, and the fourth is mix-up training. And compare our model with state-of-the-art. Our model is generally a very simple architecture, but with the power for PSLA, we will achieve the new state-of-the-art even without ensemble. That means our model performs better and is smaller than previous methods. So the key conclusion of this paper is that training techniques does matter. So that's all I have for this project. We have our code released in the GitHub. Please check our paper for the link. Thanks.